Hello everyone. I would like to talk to you about the work that we did in the lab on a specific scientific application called OMEN. OMEN is a quantum transport solver and has been nominated as a finalist for the Golden Bell Award 2 times in the past, and finally last year with this work it won the award. We optimized OMEN with the assistance of a data-centric framework that we have been developing in the lab, and we were able to achieve up to 2 orders of magnitude better performance on the Summit supercomputer. So let me guide you through the process of achieving those results. Electronic devices, from the servers in data centers to our smartphones. We use them every day, all day, and our life literally depends on them. Now, if we look inside these devices, we will find numerous electronics components, which in turn consist of billions of nano devices, nanotransistors. Therefore, it is imperative that we continue to improve this nanostructure so that our electronic devices become over time faster, potentially smaller, and also more power efficient. Continuing from this last point, let's have a look at the CPU power density trends of the last few decades. More than 20 years ago, we already reached values that correspond to a hot plate, and shortly after, people tried making their breakfast literally on top of CPUs. Now, if we had continued at the same pace, we would have already surpassed values that can be found in nuclear reactors. Now, this did not happen because around the year 2005, we reached the end of Dennard scaling, which started what we call the multi-core crisis, an era of power-efficient multi-core processors that are unfortunately slower in sequential performance. So why did Dennard scaling end? Because we started making transistors so small that quantum mechanical phenomena became dominant. Now, on the left part of the slide, you can see a drawing of a FinFET transistor, a fin of the transistor to be exact. So in the middle in blue we have the gate, while left and right is the source and the drain. And everything is wrapped around in a high K dielectric. Now, if we look closely inside the channel of the transistor, we will see how it actually works. So the channel has what we call a conduction band edge that can act as a barrier. So when the transistor is on, the carriers of the current, for example electrons or holes, let's say electrons here, have high enough energy that they can cross the channel because they travel, let's say, above this conduction band edge. Now when the transistor is off, the electrons have low energy and the edge acts as a barrier. It doesn't allow them to traverse from the source to the drain. However, due to quantum mechanics, there is a very small probability that an electron with low energy will still be able to cross through. This is what we call source-to-drain tunneling. Now, the problem here is that as we make the transistor smaller, the same happens with the conduction band edge. It becomes more narrow, and the probability that tunneling will occur increases. And this creates current leakage and increased heating of the material. Of course, we don't give up. Material scientists and semiconductor companies continuously try to find solutions. They come up with new transistor designs and materials, but they need our help. They need to be able to understand how these nanotransistors exactly work, what are their characteristics. So here is an animation that shows what we want to find out. So we need to know what is the characteristic current and voltage curve of the transistor at the gate. However, what we also need to understand is how the material heats. So what is the temperature in the channel and different parts of the channel while there is current crossing it. So This way we can evaluate these new transistor design and materials on how power efficient they might be. So how can we find the characteristics of the transistors? As with everything, either we have to build it and test it, or perhaps we can simulate it. And this is exactly what quantum transport simulation is. So let's go again inside the channel of the transistor and try to see exactly what's going on. So let's assume again that the carriers of the current are the electrons for simplicity, and they have energy, but they also have another quantity called momentum. Now the momentum is basically an angle. It's the direction of the electrons while they traverse the channel. Now in a simplified model, we make the assumption that the electrons do not interact with anything around them. Therefore, they can cross the channel and keep the same energy and momentum from start to finish. This is what we call the ballistic transport. Now, if we want to make a more accurate simulation, we can make this assumption. So let's have a look at what actually happens in the channel. So as the electron traverses the channel, it may interact with some particles that we call phonons. Now, the phonons are the result of crystal vibrations and are responsible for the heating of the material. Now, what can happen is that an electron absorbs a phonon and then moves to a higher energy state, or it emits one and moves to a lower energy. And at the same time, it can also change its momentum. Now, this more accurate mode of simulation, this is called incoherent transport. So how we can perform quantum transport simulation? What is the workflow? We start with a density functional theory application, CP2K to be exact, and we use it to create the input parameters of the simulation. So these are Hamiltonian and Hessian matrices. We use such an application because we need an ab initio model. There are empirical models, but they lack the accuracy required to simulate transistors at the nano level. Now, after we get the input parameters, we move on to the actual OMEN application. Now, this application consists mainly of two components, and the first one is called non-equilibrium Green's function solver, NEGF for short. Now, this component produces the density of the current, and then there is a Poisson solver that computes the electrostatic potential. Now, these two components are executed in iteration until the values converge. Now, a note about the runtime of this workflow. The creation of the input parameters takes less than 1% of the runtime, and also these parameters can potentially be reused for multiple simulations, so this can be further amortized. Now, the Poisson solver has a negligible performance cost, so the whole bottleneck of this workflow is on the NEGF solver, and this is why it's the focus of this work, so this is what we try to optimize. Now let's have a look at the model that the OMEN application actually implements. And let's start with the most important simulation parameters. What OMEN does is to simulate the channel of a transistor, and the dimensions of the channel depend on the exact simulation that we want to do. However, it's worth to note that if we want to simulate a state-of-the-art transistor, then the width of the channel must be at least 4 nanometers. Now, in this channel, we actually simulate atoms, and for a highly accurate simulation for this kind of dimensions, we typically need 10,000 or more atoms. Now, each atom has a number of neighbors, and we have to model their interactions, and generally a good value is 30 or more neighbors. Now, each atom consists of electrons and phonons, so we also have to model this. For the electrons, we use a model for the number of orbitals of the atom, and this is typically 10 or more. while we have 3 phonons. Now, the number 3 corresponds to the 3 degrees of freedom that each atom has in the crystallic structure to vibrate. So OMEN actually simulates separately a version of the slice for the electrons and a second version of the slice for the phonons. Now, as we said before, the electrons have energy and momentum. So what happens is that we duplicate these slices for the number of the momentum points of these particles. And if we want to have a very accurate simulation, this has to be about 20 or a bit more momentum points, while we also duplicate them for their energy for the electrons. And for the phonons, we have their frequencies. So the electron energies have to be 1,000 or more, while the phonon frequencies ideally 50 or more. Next, let's have a quick look at the mathematical formulation of the problem of the NEGF solver. Now, this solver has 2 main phases. The first phase, it's called the Green's functions phase because we compute the Green's functions. So we have a set of G values for each electron energy momentum point and a set of D values for each phonon frequency and momentum point. In this phase, we also compute the current that crosses the channel of the transistor. Now, we take these Green's functions and we use them in the second phase, which is called the scattering self-energies, because we compute these quantities of the same name, and these are the capital Greek sigma and pi. We use these scattering self-energies in the next iteration of the Green's functions phase in order to get a more accurate estimation of the current. Now, these 2 phases continue to be executed one after the other until the value of the current converges. So let's see now how OMEN implements this mathematical formulation. So it takes these duplicated slices that we saw earlier and arranges them to 2 grids, one for the electrons and one for the phonons. Then it takes whatever compute resources are available, or computing nodes, for example in a cluster or supercomputer, and assigns to each one of them a set of these slices. So this happens in the following manner. So, quick example. So the first, let's say, node will be assigned the first 2 slices for the first momentum point. Then the second node will be assigned to the next 2 slices, and the third node will take the remaining slice from the first momentum point of the electron grid. And then we proceed with the next momentum point, and this repeats until we cover the whole grid. And the same happens for the phonon grid as well. Functions phase. Now, each compute resource is doing an invariantly parallel computation of the Green's functions for the slices that it has been assigned to. And only at the end we have a reduction to compute the current. On the other hand, in the scattering self-energies phase, things are a bit more complicated, so I will try to show you with an example. So let's look at the electron grid and specifically at the dark blue slice. So then we also select a slice from the phonon grid, so the dark red one, and then we compute what will happen to the electrons of this dark blue slice if they absorbed or emitted the phonons from the dark red slice. And we end up with 2 cases that are represented by the 2 green slices. So what happens is that the data of these slices are sent to the node that is responsible for the dark blue slice. And then a local computation happens and some data are sent back to the node that is responsible for the red slice. Now, the same thing happens in rounds. So we move on then to the next phonon slice, and we do the same. And this process continues until we cover the whole phonon grid. So in total, for each electron slice, there is this stencil-like communication pattern that has a size of 2 times the number of momentum points times the number of phonon frequencies. Now, if we put it all together for the whole electron grid, we can see that we have a communication cost that is quadratic to the number of momentum points, and this can be a bottleneck. Before we proceed with how this is a bottleneck and what we can do about it, let's first have a look at what we believe to be a common pitfall in the development of scientific applications like OMEN. In order to develop a scientific application, you will usually assemble a team of domain scientists and performance engineers, or in general people that are proficient in computer science. Now, of course, many times it happens that a single person does everything, and we call this person a computational scientist. However, even in this case, there are 2 distinct roles. What happens is that the domain scientist contributes with a mathematical formulation of the problem, while the computer science, the performance engineer, are responsible for developing this application in a language suitable for high-performance computing, like C++, and they also have to use the required libraries for inter-node communication, like MPI, or use of accelerators, so for example CUDA for NVIDIA GPUs. Now, all of this work goes into the same code base, and the problem is that as time passes and there are new models and algorithms added and optimizations being implemented, this code base grows very large and sometimes becomes what we call spaghetti code that is difficult to maintain, but more importantly, it's difficult to add new models and also optimize it for emerging computer architectures. Now, to solve this problem, we suggest the use of a framework that fundamentally separates how these 2 categories of scientists work, the domain scientist from the performance engineer. So what is this data-centric framework? We start with the domain scientist who is responsible for the problem formulation. Now, the domain scientist is also expected to write this formulation in a high-level program, like for example in Python, which is a language that is very popular now with domain scientists in general. Now, this high-level program is automatically converted to a data-centric intermediate representation, which I will describe in more detail shortly. At this point, the performance engineer takes over and applies graph transformations in this representation in order to optimize it. And at the end, code generators generate optimized code for the target architectures, like for example NVIDIA GPUs. So this is exactly what we did for the OMEN application. So we started with the original application, which has probably more than 50,000 lines of code, and we focused on the NEGF solver, which has about 16,000 lines of C++. And then we used our framework to rewrite this application in a Python frontend in about 3,000 lines of code. And then we took performance critical kernels, we converted them to this intermediate representation, we optimized them, and we ended up with about 2,000 nodes. Let's proceed with the basic elements of this data-centric intermediate representation. So we have the oval shapes that we call access nodes, and they represent the data that are being read and written by the application. We have nodes that we call tasklets, and they are fine-grained stateless computations. They can also abstract away more complicated computational kernels. We have dataflow that is represented by the edges of the graph, and these edges have annotations that we call memlets, and they show at all levels the exact subset of the data that is being accessed. We have states, the big blue rectangles, and there can be edges that connect the states and are annotated with control flow. Finally, we have an abstraction for independently parallel computation. If you look in the graph, we have two more special nodes called map entry and map exit. Together, they define what we call a map scope. So whatever is in a map scope is executed independently parallel as many times as it is shown on the index space of the map. So here we have the indices I and j, and we have a total of about MN iterations. So for simplicity, you can also imagine that it's like a parallel for loop. So let's see how OMEN looks in a data-centric representation. So we have two states, one for the Green's functions on the left and one for the scattering self-energies on the right. Let's first focus on the left states, on the Green's functions. And here we can see that we have two map scopes, one for the electron grid and one for the phonon grid. You can see if we look at the indices of these maps, we can see that we have this independent computation per slice. So it's per momentum and energy point. Now, if we focus on the right state, the scattering self-energies, we will see again that we have a map scope, but now here we have a lot more indices. So we have again the electron, energy, frequency, momentum indices, but we also have this A and B, which are the atom and neighbor dimensions. So therefore we can see that there is greater parallelization potential that perhaps we can exploit to optimize the application. Now let's start optimizing OMEN, and let's start with the Green's functions phase. So now we have again the Green's functions phase, and this time we omitted the map scope for the phonons for brevity, because imagine whatever happens for the electron grid happens also for the phonon grid. So here we have a bit more detail in what actually happens. So there is this input Hamiltonian matrix that for each energy and momentum point has to be specialized, and then we also have to compute some boundary conditions. Now what is interesting here is that this computation, the values coming out of these kernels, is actually independent of the iteration. So every time that the Green's function is computed, the output of these kernels is actually the same. So an obvious question that perhaps you will ask is, okay, then why do we have to compute them every time? So we can actually fix this with a simple data-centric transformation. So what happens is that we actually create another state that is executed once before we start the iteration over the Green's function scattering self-energies. And this phase, what it does, it basically computes all the specialized Hamiltonians and boundary conditions for all the different momentum and energy points. Now you might ask, though, okay, this is kind of obvious, why wasn't this done in the original OMEN application? Well, there are some issues here. So these specialized Hamiltonians can actually be 3 GB per energy and momentum point, while these boundary conditions add another 1 GB. So the obvious problem here is that it's possible, depending on our resource constraints, that actually this cannot happen. So the idea here is that the data-centric frameworks allows us the flexibility to somehow control this. So we actually made a number of different schemes here. So we decided to not cache anything, so every time to recompute all the values. Then we had another scheme that we basically cast the boundary conditions that only cost a gigabyte per momentum point, and a final scheme where we cached all of them. Next, we want to optimize individual operations and specifically sparse operations. So here we have a code snippet from this RGF kernel in Python. So here you can see that this is a very common pattern where we have a multiplication of 3 matrices. And what is interesting is that the middle matrix is dense. However, the left and the right one are sparse and can be given either in CSR or CSE format. So what we did is that we profiled on the summits of computer that we actually run our benchmarks, these operations in order to see what is the best way to optimize this operation. So we tested the GEM kernel from the kublas library, but also the CSRMM and GEMI kernels from the Sparse library. So the CSRMM multiplies a sparse matrix on the left in CSR format with a dense matrix on the right, while the GEMI kernel multiplies a dense matrix on the left with a CSC matrix on the right. And of course, here with the help of transpositions, we have a number of different options. So we found that the best case will be to use, if possible, the CSRMM kernel in NT operation. So the left matrix to be non-transposed and the right transposed. And then we came up with different schemes of implementing this double multiplication. So we tested the approach of just using kublas. So in this case, we just convert everything to dense and we do dense multiplications. And then we also came up with two different approaches that combined the Sparse kernel, and we were able to find an approach that used two calls to the CSRMM kernel, and we got, as you can see, a very big speed up. A useful feature of the data-centric framework is that it helps us to automatically extract parallelism. So here we have another code snippet from the same RGF kernel. And you can see here that we have these multiplications, that it's probably simple for a human to see that they are independent and therefore they could be computed in parallel. So now if we look at the part of the graph that is generated from this code, we will see that we have these two operations here. And in the graph, the framework can detect that these are independent. And then in the code generator, it will automatically create the required codes for assigning these computations to different streams. It will also output the required synchronization code. And then we can see also, so this is a screenshot from the NVIDIA profiler, that it's possible to actually have these operations computed in parallel. Now let's proceed with optimizing the second phase, the scattering self-energies. And here we want to showcase how we can optimize coarse-grained data movement. So if you remember from the previous slides, in this phase, it is where we have this complicated stencil-like communication pattern with this quadratic factor. So first of all, we need to be able to model the communication that is happening in this phase. And we do this with natural loop tiling. So it's basically like tiling a for loop. So we take the map scope and we split it to two nested map scopes. And the outer map scope is iterating over the tiles, or perhaps the computing nodes that we are running the application node, while the inner scope is iterating over a single tile. I mean, in other words, the workload of a single node. Now, these scopes are connected by edges that are automatically annotated by the memlets. And the expressions of the memlets, the subset of the data, basically represent the surface of its tile. So this is the communication volume needed for each node. So we can take these expressions and we can use them to create a model for the communication. And then we can use this model to, for example, try to find the optimal tile sizes to minimize the communication volume. As an example, let's have a look at what is implemented in the original OMEN application. So as we saw before, its computing resource is basically assigned a subset of the energy. So we have this tiling by energies for a specific momentum point. And also, as we saw before, this results in this stencil-like pattern with a communication volume that is quadratic to the number of momentum points. Now, with the data-centric framework, simply by changing the tile sizes, we can very easily explore different decompositions. So, for example, we could try to tile by atom. In order to understand better what will happen in this case, let's have a look at a simple example. Let's say we have 4 computing nodes and each node is assigned a single slice. So what we do is we split those to tile of atoms, and then with perhaps all-to-all operations, we rearrange these tiles. And now each computing node can compute the scattering self-energies for itself without any further communication. And what happens here is that we studied this from a mathematical point of view, is that we basically remove the quadratic factor. Now, to showcase the viability of this approach, here is a graph of the communication volume per iteration in terabytes for different number of momentum points for a simulation that we did with both the original OMEN application and the data-centric framework. And we have the original OMEN application in blue, and you can see that as the number of momentum points increases, we have this quadratic growth, while we have the data-centric version in red, which remains basically flat. And in the last data point for 11 momentum points, the difference is almost an order of magnitude. Now, something important. The takeaway here should not be that the original OMEN application had a wrong decomposition of the scattering self-energies phase, because there is no right and wrong. What we have is a best decomposition that depends on the simulation parameters, but also on the machine that we are running the simulation on. So let me try to convince you for this with a hopefully intuitive example. So let's say that we are doing a simulation on a slice of 10,000 atoms. And we are running this simulation on a cluster with 100 nodes. This means that we will have tiles of 100 atoms per node. And of course, this works very well, as you can imagine. But now we want to run the same simulation on another machine, let's say the Summit supercomputer, which has about 27,000 V100 GPUs. So we want to split these 10,000 atoms on 27,000 GPUs. And obviously we have a problem here because it's not easy to split an atom to multiple nodes. And the answer here is very simple. So we go back to our model with the tile map, the 2 nested map scopes, and we change the decomposition. So for example, we can tile by the atoms, but also we can tile by the electron energies. And perhaps we can find that in this case, this provides the best decomposition. But really the strength of the data-centric framework is in being able to easily change this, that we have this flexibility that allow us to change this, not be fixed. Next, with the data-centric framework, we can also optimize fine grain movement. So here in this data-centric representation, we have again the scattering self-energies phase with a bit more details. So in this kernel inside here, we can look that we actually have 3 main operations. So we have 2 matrix multiplication and an array scalar multiplication. And perhaps we want to focus on each one of them separately. So with a data-centric transformation, what we can do is what we call map fission, and basically break this map scope to 3 separate ones, one for each operation. And then we can focus, for example, on the bottom one. Now, if we look at what is happening here is that we have a lot of small matrix multiplications. However, if we look closely at the algorithm and at the graph, what is interesting is that we don't want to compute the individual products of these multiplications, but rather we want their sum. So perhaps there is something that we can do here. And next, we can do data layout transformations, which means that we basically take these matrices and rearrange how they are stored in memory in order to allow for better memory accesses. Then we can also see that there is a kind of a pattern for these multiplications, that we basically have rows of matrices that are multiplied with columns, and we can do some clever linear algebra here and combine multiple of those multiplications in a single kernel. And finally, after we optimize all these different maps together, we can put them back with map fusion, and this is an example of how this will look like. Now let's focus a bit on the spatial kernel that we exposed on the previous slide, where it does a lot of this matrix multiplication in a combined kernel with a strided pattern. And we want to find what is the best way to implement it. So first, we can look at an optimized library from the vendor, so cuBLAST in this case, which actually has an operation for that. So there is this gem strided BATS kernel in the cuBLAST library. And in double precision, this has some performance that we perhaps want to see if we can do something better. So what we can do is we try to make an implementation with a data-centric framework, and we were able to get a speed up of about basically almost 7 times. Then in the V100 GPUs, we also have this tensor cores that they do computation on mixed precision. So we wanted to check whether it was possible to use those to get even better performance. So we created, again with a framework, this specialized kernel in a way that uses the tensor cores, and we were able to get another speed up of 5. Now, I want to say here that it's in scientific applications, you need very high accuracy usually, so many times double precision. So it's not that simple to just, let's say, downgrade your accuracy in a specific kernel and say, okay, yeah, this runs and it's fine. No, it's not. So what we actually did is that we studied the values of the inputs and outputs of these kernels. And based on those, we made some normalization schemes. And we were able to show experimentally that this did not harm the accuracy of the output on the current of the channel. So let's put now all of those together, and let's see how the data-centric implementation of OMEN stacks up against the original OMEN application in performance. So we start with a simulation of a slice that is a bit small. So we have length of 35 nanometers, and the width it's only 2.1 nanometers. So this is much less than the 4 nanometers that was mentioned earlier. And here we have a number of atoms that is a bit less than 5,000. So we are also lacking in this department when it comes to simulation values required for a state-of-the-art, highly accurate simulation. The number of neighbors was 34, which is a good number. The electron energy is 700, which is lacking a bit. And the number of frequencies, 70, which is good. So first we did strong scaling results with 7 momentum points. Now in blue we have the times for computation for both versions of the program, and in red we have the times for communication. Now the 2 top lines correspond to the original OMEN application, and the 2 bottom lines to the data-centric versions. So this is a graph of time versus number of GPUs used on the Summit supercomputer. So you can see that the data-centric framework, it's much faster. And on the last data point, we have a speed up of about 17. Then we moved on with weak scaling results. So we changed the number of momentum points from 3 to 11. And again, you can see that the two top lines is the original OMEN application, and the two bottom lines is the data-centric framework. Again, much faster. At the last data point, a speed up of about 25. Now, the simulation that we just showed was basically very close to the limit of what the original OMEN application could simulate. However, we wanted to go beyond that, and we actually wanted to do a highly accurate simulation for a realistically sized transistor. So we did another simulation on a similar slice, where now the width of the channel was 4.8 nanometers. So this is a very good value, and this increased the number of atoms to a bit more than 10,000. We also did this on 21 number of momentum points and about 1,200 electron energy. So all the simulation parameter values are exactly what we need for this highly accurate simulation. And now we run this on the summer supercomputer for a different number of GPUs used, up to basically almost the full extent of Summit. And you can see in blue that we have the version of the application that everything ran in double precision, while in red it's the version where we had this special kernel that was running on the tensor cores in mixed precision. Now here we also use the different caching scheme that were shown previously. So for the lowest number of GPUs, we had no cache because there was not enough memory to cache anything. Then in the next data point, we cached the boundary conditions, and in the other 2 points, we cached everything. Now, at the full extent of the supercomputer, we were able to achieve about 85.5 petaflops per second. So this is about 58% of the Limpac performance of the machine. And in mixed precision, that was almost 91 petaflop per second. The main bottleneck of the original OMEN application is really the number of momentum points. So as this simulation parameter is increased, it really makes it harder for the original OMEN application to keep up. For this reason, we wanted to find a way to directly compare the original OMEN application with the data-centric framework in a simulation where we use 21 number of momentum points. So to that end, we made the third simulation where we created a very small slice with only 1,000 atoms, but the rest of the simulation values are the same as before. So what we did is that we ran the simulation on the original OMEN application with almost 7,000 GPUs on the Summit supercomputer, and we compared this to the data-centric framework running the previous simulation on the same number of GPUs. And what we found is that the data-centric version was basically able to simulate 10 times the number of atoms in less than a tenth of the time. So we had an overall speed up that is more than 2 orders of magnitude. To recap and conclude, we saw the heat dissipation issue in today's computing architectures and nanotransistors. And we saw that quantum transfer simulation is a tool that can assist us to find solutions. Next, we saw a specific application that does this simulation, OMEN, and we saw the domain scientist view and the data-centric view of the application. And next, we saw how we can use the data-centric framework to optimize coarse-grained and fine-grained data flow, and also automatically extract parallelism. And finally, we saw that we were able to get great performance improvements following this approach. Now for OMEN, the models already implemented can also be applied to other types of nano devices, so not only transistors, but for example, perhaps diodes. While the lessons learned from the data-centric framework can be used to other scientific applications, and why not, perhaps get similar performance improvements.